This time our problem is encodes complicated mass-pulley system. Now this is one of the harder problems, and well, the algebra is a little more difficult than other problems. Plus, it's kind of hard to keep track of direction, so we'll try to be careful with that. You'll see why in a minute. So the setup itself does not look too complicated. So we have a pulley up here fixed. You have your rope, okay, which is connected to a mass M over there. Now, so let me try to get the dimensions right. The height here is h, and the distance from here, this distance, I'll label as x. So you essentially keep a constant tension on the string. What we're trying to find here is going to be the acceleration. Now, so part A, we're asking the acceleration. In part B, we'll try to sketch the acceleration again. And in part C, we'll try to find the maximum acceleration in there. Of course, while doing B, we might actually have to find C anyway. In finding the acceleration, we'll try to find it as a function of x, where x is this distance. And of course, other given constants, like it's going to be a function of x, m, h, g. And we also have kinetic friction here, mu. So, no, do we have friction? Yes, we do. Of course we do, yeah. And the constant t, yeah. 1, 2, 3, 4, well, how many? 6 parameters total. In fact, well, 5 of them are constants. The x is the only variable we're trying to solve acceleration in terms of. So how do you go about solving this problem? Now, obviously, you have your tension there. Now, it's very convenient to introduce the angle theta into the question and do the solution in terms of that until you're very close to the end. Otherwise, it gets really sticky. So if I define that angle theta, I can draw the free body diagram for this mass. If I take that, what forces are acting on it? First, there is mg, the weight of the object, pulling down. I have the normal force pointing up. I have the tension, T, which with an angle theta there. What else? I have the force of friction. Now, well, obviously the object is going to be accelerating to the left, so I expect the force of friction to be acting towards the right. Now, the overall acceleration, I'm going to define, I will take right as the positive direction. As I say, you have to be careful. You can get the wrong signs. So I will define A to be positive towards the right. Okay? So now I can write the equations of motion in the x and y directions. Except t, everything is parallel to my, if I take x and y like that. Everything is parallel to my axes. So I will have to separate just t to its components. This is going to be t sine theta, and this component is going to be t cosine theta. Now I need my equations of motion. First one is in the x direction. I have the force of friction, positive, minus t cosine theta equals mass times the acceleration. And that's it, right? Yeah. And in the y direction, I have n plus t sine theta minus mg. Since I'm assuming no acceleration in the y direction, this is going to be 0. Well, of course, one thing I didn't mention is we have an additional assumption here. That is the force T is not enough to lift the object at any position during the motion. All right, then let's see. What am I trying to solve for? T is known. OK, so I'm trying to solve for the acceleration. I need to find the force of friction. Of course, the force of friction is just going to be mu n. What is n? N just drops from there, is mg minus t sine theta. So force of friction is mu mg minus mu t sine theta minus t cosine theta equals mass times the acceleration. So far, so good. If I want to get the acceleration out of this, I'm going to write, I want to leave m alone in the denominator, so I'll keep it everywhere else. So I have what? I have mu mg minus t cosine theta plus mu sine theta. Now, the equation is correct. However, I want to make sure I'm understanding what I'm doing. Now, I defined acceleration to be positive towards the right. So the thing is pulling it to the left, so I expect this to be negative, right? Given the mass is far away to the right. So, so the acceleration is going to be negative for most of the motion. However, well, does this solve part A? Not quite, because I have introduced theta on my own in addition to these. So I have to say what cosine theta and sine theta are. So cosine theta is from here. So I have from this triangle, this is h, this is x. Cosine theta is x over square root x squared plus h squared, and sine theta is h over square root x squared plus h squared. I could substitute that there, but I'm going to leave it as an exercise for the student. It's just going to take up valuable board space. Now, so the thing is, why are we trying to sketch the acceleration? Well, we're trying to understand how it behaves. So how do you go about sketching this? So I need to erase something. So I can erase this part now that I have the equation. All right, so if this is acceleration, and that's your x-axis, given you are very far to the right, where x is close to infinity, what would the value of the acceleration be? Now, at the very right, what is cosine theta and what's sine theta? Cosine theta is going to be essentially 1. Because, well, if you think about it, if you move it to the right, the angle is going to get narrower and narrower. It's going to approach 0. So essentially, as in the limit, as x goes to infinity, so to speak, cosine theta here is going to be 1, and sine theta is going to be 0. So in this case, at infinity, you get for a at x approaching infinity, you get, so this term is 0, so you get just t mu mg minus t over m. Now, the question is, this is supposed to be negative, is it? Well, the thing is, if this, so consider t minus mu mg. If this wasn't positive, the mass wouldn't be sliding. So I can write this as minus t minus mu mg over m, where this quantity is greater than 0. So as x goes to infinity, you have this. So it's just mu mg minus t over m. So you're going to start from here. What's the behavior at exactly x equals 0? At x equals 0, your theta is essentially 90 degrees. It's pi over 2. In which case, your sine theta becomes 1, and now cosine theta is 0. So as the acceleration at x equals 0 is going to be what? It's mu mg minus mu t over m, which is what? In mu parentheses, t minus mg over m. Now, this one, is it right?
Negative sign, maybe. Could you check the sign?
The sign is with, wait, mg, is the sign correct? Yes, so I have, okay. I got it backwards. I turned it around for some reason. Fix that. So it's mu mg minus t over m, right? So, and this quantity is actually positive. Why is it positive? Well, we said the force is not strong enough to lift the mass, so that's exactly that condition. If t was greater than mg, this would have been negative, but it is not. It's not. If it's not lifting the object, so when you reach this position with the mass, the rope is pulling straight up. So there is no force which is actually pulling the object towards the left. The only thing left is the force of friction, which is going to accelerate it towards the right. So it's going to slow down, no matter what, when you reach the center. So at exactly x equals 0, you're going to have mu mg minus t over m. So if you start over there and end over here, there are, well, quite a few things you can do in the middle. But we did plot this, actually. So we kind of do know what happens. So the real thing that happens is something like that. You can try plugging in some values and plotting it yourself. And there is, well, we called it a maximum. It's a magnitude maximum because it accelerates to the left. The question is, what would that be? So that we can find. I did destroy my equation a little bit, but it's still alive. I want to find what this point is. At what value do I get the maximum acceleration towards the left? So that involves taking the derivative of this with respect to x. But since theta is just a function of x, I could take my derivative just with respect to theta. And it makes things much simpler. So what I'm going to do is first I'm going to get rid of my figure. OK, now I'm going to, now the thing is, you can take the whole expression, but if you, just by inspection, I can see that everything else except this part here is a constant. So all I have to do is find where the maximum of this thing is. So I just need to take derivative with respect to theta of the theta of cosine theta plus mu sine theta. And I'm going to set that equal to 0. So the derivative is, this is cosine theta, derivative is minus sine theta, plus mu, derivative is cosine theta, equals to 0. So I get sine theta equals mu cosine theta. So tangent theta equals to mu. Tangent theta is what? It's, since tangent theta, you can just see from the equations there, cosine and sine, without even referring to the figure, it's just h over x. So the point of maximum acceleration happens when mu equals h over x. So just for solving for x, I get this happens when x equals h over mu. Now the question is, what is the value of the acceleration there? All right, so I'll have to calculate that animal there. So it's mu mg minus t. Cosine theta, I have x over square root x squared plus h squared plus mu h over square root x squared plus h squared, right, over m. All right, now I'm going to plug in h over mu for x. It's h over mu over square root h over mu squared plus h squared plus mu h over square root h over mu squared plus h squared. So I'm going to put the 1 over m over here. Are we going good so far? So far, so good. All right, so I need more board. All right, so I have, that is what? 1 over m mu mg. I have minus t times. Now, in the bottom here, there's h squared, h squared, h squared, h squared, and h's. These cancel. So you have a 1 there, and that cancels. You have a 1 there. So I end up with what? And that h also cancels. So I have a t parentheses. I have a in the numerator, I end up with mu plus 1 over mu over square root, what? 1 over mu squared plus 1. Interesting thing is we have lost all reference to h. So no matter how high your rope is, your pulley is at the start, you end up with the same value. You can actually simplify it a little further, but I'm not going to force that any further. So that would be your value. If you plugged in, you can actually see that it's a greater negative value than the original one. Anything else we didn't solve for? That's all. Yeah.